Hello everyone and welcome back. So today what we are going to do is we are going to learn about 2D frames, and this lecture is going to help you also with the Matlab project, like the second part of the Matlab project in which you will implement 2D frames in your codes. So let's get started. So actually, we have already considered beam element stiffness matrix. And if you recall, for a beam element, we have considered 4 degrees of freedom. And the degrees of freedom were actually VI, theta I. So this is a vertical displacement, rotation at I node, and the vertical displacement at the root and rotation at the J node. And important thing is, for a beam, we always consider the left node at I node and the right node at J as J node. So you can see that we are working in the local coordinate system, because local coordinate system goes from x-axis goes from I node to J node, and the y-axis goes is actually oriented if you move anti-clockwise in 90 degrees from x-axis. Okay, so for beam element we are always working in the local coordinate system. And that was the reason I was using this notation of bar. So the bar, overhead bar, indicates we are working in a local coordinate system. So you can see that for a beam member, we can write a stiffness matrix that is a 4x4 stiffness matrix. And we have derived this stiffness matrix by solving the differential equation of the beam member. And finally, we can actually express the nodal forces in terms of the nodal displacement vector. So nodal forces will be Pyi, Mi, Pyj, Mj. And they're also expressed in local coordinate system. So Pyi is actually oriented towards the local y-axis. And similarly, Pyj is also oriented towards the local y-axis. And theta I and theta j is actually, we are using the right-hand rule. So using the right-hand rule, the z-axis is actually coming out of the screen. So you can see that the orientation of the positive direction is actually by using the right hand rule. It turns out to be anti-clockwise direction is the positive direction. So both movements and rotation follows the right hand rule, and so the positive sense of these movements and rotations is the positive z direction. And now what we want to do is we want to actually add the axial degrees of freedom to this beam element. And we have also already talked about that the axial effects are uncoupled with the flexural effects for a beam element. So if we work in the local coordinate system, it turns out that the axial effects means we are looking at the effect of the axial degrees of freedom. Here I'm calling ui and uj are the axial degrees of freedom. You can see that I have added 2 more degrees of freedom here compared to this case, where we have only vi, theta I, vj, and theta j. And now I have added uj and ui and uj also to this beam element. So ui is the horizontal displacement at the I node, and the uj is the horizontal displacement at the j node. And we want to find the stiffness matrix of this kind of element. So now we are going to order the degrees of freedom as follows. So degrees of freedom ordering is ui, vi, theta I. So you can see that u displacement first, v displacement second, and the theta displacement the third at the I node, and the same thing at the J node. And similarly, accordingly, we order the forces. So forces are Pxi, Pyi, Mi, Pxj, Pyj, Mj. So you can see that Pxi and Pxj are actually the axial forces, and Pyi, Pyj are the shear forces at the end of the beams. And similarly, Mi and Mj are the moments. And it turns out that the stiffness matrix is actually, what we have to do is we have to just add the stiffness coefficient for the bar member, because in the axial direction, this member is just a bar member. Okay, because axial and flexural effects are uncoupled. So we can just take the bar member stiffness coefficients and add to this matrix. So what I have done, I have taken this stiffness matrix, expanded to 6x6 size, and for Pxi and Pxj, you can see that I'm just putting the bar members, bar element stiffness matrix. So the stiffness coefficient I'm putting are Ea by L minus Ea by L, Ea by L minus Ea by L. And you can see that Pxi only depends on ui and uj. It does not depend on the flexural degrees of freedom like Vi, theta I, Vj, theta j. So Pxi is minus Ea by L times Vj, Uj, plus Ea by L times Ui. So it only depends on Ui and Uj degrees of freedom. Similarly, Pxj only depends on Ui and Uj degrees of freedom. It does not depend on any other degrees of freedom. And if you look at the Pyi, Mi, these forces and Pyj, Mj, they don't depend on Ea by L, okay? They only depends on the beam stiffness coefficient. So that depends on these numbers, because you can see that all these corresponding entries to Ui and Uj are all 0. So we have just added the bar member stiffness coefficient to make this as a 6x6 stiffness matrix. So this is actually a beam element stiffness matrix where we have included the axial degrees of freedom. This is important that because for the frame member, we have to consider all axial degrees of freedom also. Now, what we want to do is we want to write down the equilibrium for the beam element. So you can see that we want to consider total forces for a beam element. So total forces is forces due to the member forces, because there can be some member loads acting on the beam, plus the displacement. So again, we are using the principle of superposition here, and then we are saying the total forces for the beam is the sum of forces due to displacements plus forces due to fixed end whatever reactions here. So we can write the total forces. In this case, you can see that for the beam member, we always work in local. So that's the reason I'm using the bar here. So everything is a bar here. So, and PO bar, again, because these are expressed in the local coordinate system. So that's the reason there's a bar on all these quantities. And then D bar is just a Ui, Vi, theta I, Uj, Vj, theta j with all the bars, because they're still defined in the local coordinate system. And now we can write P bar is equal to K bar, D bar plus PO bar. PO bar is the fixed end forces that are already given to you. So I have given you a lot of cases with different fixed end forces. So PO bar just comes from that table. K bar is the stiffness matrix we just wrote. So this is your K bar. And this is the complete equilibrium for a beam element. And for the beam element, we always consider equilibrium in the local coordinate system. So you can see that beam element, we never have to worry about any other coordinate system. We just work with the local coordinate system. Now what we want to do is we want to take this beam element and think about, like, how can we get a frame element. So first, let's define what is a frame element. Frame element is just a beam element that is oriented at an angle, okay? So it's not like horizontal anymore. So in this case, you can see that this is what we'll consider a frame element. So it is oriented at some angle. I've not shown the angle here, but we'll not worry about it for now. So you can see that for the frame element, this is a frame element, and there is some loads acting on this element, okay? One important observation is that loads are acting in the local coordinate system, okay? So we'll talk about it in a moment. The degrees of freedom for a frame element is actually now expressed in the global coordinate system. So global x is in x direction, and this is the global y direction. So the degrees of freedom are actually Ui, Vi, theta I, Uj, Vj, theta j. So there are 6 degrees of freedom for a frame element. And what we want to do is we want to calculate all these forces here. So again, forces are also expressed in the global coordinate system. So these are Pxi, Py, Mi, Pxj, Pyj, Mj. See, these are the 6 forces. And for the frame element, we are going to arrange the degrees of freedom in this order. So we are going to order the degrees of freedom at the I node. So it will be Ui, Vi, theta I. And then at the j node, Uj, Vj, theta j. And it doesn't matter which node is I and which node is j. We can call this node as I and this node as j. So labels we can change. It's not a big deal. So finally, we are going to use the same idea. We are going to use the concept of superposition. So we're going to say that the total force P is equal to the force due to displacements plus the fixed end forces. So here you can see that the fixed end forces are also expressed in the global coordinate system. So you can see that all these axes are now oriented in the global coordinate system. And interestingly, the movement, the axis is always z direction. So we are using the right hand rule. So so the movement is always in the z direction in this case. So it's anti-clockwise if you think, because the z direction, if you use the right hand rule, that's anti-clockwise direction. And now what we want to do is we want to find what is k and what is p0. Okay, so this is what we are looking for. And somehow actually we want to get this information from the beam element. That's what we want to do. So we want to relate this frame element that we need, and we want to get k and p0 for that information from a beam element. And the idea is as follows. So if you take a beam element, you can orient it. Actually, you can rotate it. And here I am rotating a beam element to make it a frame element. But all these coefficients are still expressed, all these numbers are still expressed in the local coordinate system. So you can see that the local x-axis is from going from I to j. And these are the forces at the I node, and these are the forces at the j node. And they are still related to the displacement at the I node and the displacement at the j node, plus the fixed end forces in the same, the equation remains the same. So this is exactly the same equation as we wrote if this member was horizontal, because it doesn't matter. We can take the member and rotate it. So that does not change anything. So now what we want to do is, now if you compare this, we can think about this is like a frame element, but now we have expressed forces and displacement in the local coordinate system. And interestingly, in the local coordinate system for a frame element, it is exactly like a beam element. So this is nothing but we have taken this beam element and just rotated it. Okay, so this is just this, but we have rotated it. So the one important observation is in the local coordinate system, a 2D frame element is same as a beam element. So there is no difference between a beam element and a frame element in a local coordinate system. But we are not interested in this relationship in the local coordinate system. We are interested in to find this relationship in the global coordinate system, because this is eventually that is needed to be assembled for the global structure. So let's try to figure out how can we find the information in the global coordinate system. So to recap, what is happening? We know the information in the local coordinate system. So we know the k bar, PO bar, because k bar is just a beam element stiffness matrix. And so we know this information. And what we want to know is the information in the global coordinate system. So we want to know what is k and what is p0. And we want to find the relationship between these two local and global coordinate systems. So if somehow we can relate k to k bar and p0 to p0 bar, then we are good. So then we can go ahead and solve our problem. And this is now I want to show how can we get this relationship. And to just quickly show you that you can think that in the local coordinate system, this is how the fixed end forces are going to be. And actually, if you go back and see or check your tables, from those tables, you can see that all those fixed end forces are always represented in the local coordinate system. So if you look at the fixed end forces for the beams, these are the numbers that are given to you. But in the global coordinate system, these are the numbers we are interested in. Okay, so we are interested in the forces in the x direction, y direction, and the moment. Okay. In some sense, you can also think that these forces are just like if you take these forces and decompose in the x and y direction, like a global x and y direction, you will end up with these forces. But this is the calculation we want to do, but we want to do in a more systematic way. So in the local coordinate system, we are going to use the bar again to represent the fixed end forces. And in the global coordinate system, there is no bar. So we just represented this quantities, but with no bar. Now let's see how can we go from local to global coordinate system, or vice versa. You can also go from global to local. And we are going to again use the idea of transformation. And to use that idea, first let's define certain quantities. So this is a frame member in the local coordinate system. So you can see that this is the I node, this is the J node, and the local x-axis goes from I to J. So I have drawn a local x-axis as x bar, and Ex bar is actually a unit vector that is oriented from I to J. So Ex bar is a unit vector in the x bar direction. Similarly, Ey bar is a unit vector in the y bar direction. So we need these two unit vectors to find the relationship between the global and local coordinate systems. And this is the global coordinate system. X is oriented in the x direction and y is in the y direction. And Ex is the unit vector in the x direction, and Ey is the unit vector in the y direction. So these two vectors are also given to us. Now what we can do is, you can see that let's focus at the I node degrees of freedom. At the I node degrees of freedom, there are 3 degrees of freedom: ui, vi, theta I. And let's compare the I node degrees of freedom in the global coordinate system. The corresponding degrees of freedom are ui, vi, theta I, but here we are using bar, so they are oriented in the local x and local y direction. Here they are oriented in the global x and y directions. One important thing is clearly theta I and theta I bar, they are oriented in the same direction because they are both oriented in the z direction. So actually theta I bar is equal to theta I. So there is no change in the rotation. So rotations are exactly the same. So theta I bar is actually equal to theta I. Similarly, theta j bar is equal to theta j. So rotations are same. So rotations are not changing in this local and global coordinate system. And now what we want to do is, we want to write the displacement in the local coordinate system at the I node. So you can see that the displacement di at the I node is actually given by, we are writing in a vector form. So vector, if we want to write in the vector form, we can express like this. So we can write ui bar times the unit vector in this direction plus vi bar times the unit vector in the y bar direction. So this is the vector representation of the displacement at the I node. Similarly, in here we are representing the vector in the vector form, the displacement at the I node, but using the global basis. Global basis is Ex and Ey. So we are writing di is equal to ui Ex plus vi Ey, because ui is the displacement in the x direction times the unit vector in the x direction plus the displacement in the y direction, global y direction, vi, times the unit vector in the global y direction. And more importantly, because these are two vector forms, they are the same displacements. So we can write di bar is equal to di, because exactly the displacement is not going to change. So in the vector form, we can write, we can make these two displacement vector equal. And similarly, the same exercise we can do for the displacement vector at the j node. So we can write exactly the same relationship, dj bar is equal to dj. And this is an important observation. So if we write anything in a vector form, we can make them equal. And from here, we can actually derive the relationship between these coordinates. So we want to get the relationship between ui, vi, and here ui bar, vi bar, and ui and vi. So we are going to get it from this relationships here. So let's see how can we do that. So first of all, what we have to do is we have to figure out what is that Ex bar and Ey bar, these unit vectors. So let's do this first. So Ex bar is nothing but ER. ER is the unit vector that we already, if you go back to your lecture notes on 3D trusses, we have learned about transformations. So you will find the definition of ER there. So this is the vector we defined in that lecture note. So this is the unit vector from going from I to J. And this is just nothing but lambda x Ex plus lambda y Ey. So this is our Ex bar vector. To find Ey bar vector, we are using one trick. So we are saying that Ey bar vector is Ez cross Ex. So here we are using the cross product. So if you think that EZ is the unit vector in the Z direction. So it's coming out of the screen. And if you take the dot cross product of EZ cross EX bar, you will end up with EY bar direction. So we use this trick to find EY bar. And when we are doing this cross product, this is just a simple cross product, we are using these rules. So we already know the cross product rules, that EZ cross EX is equal to EY and EZ cross EY is equal to minus EX. So using these two rules, we can simplify this algebra here. And if you simplify this algebra, you will find that EY bar is minus lambda y EX plus lambda x EY. So now we know what are the unit vectors in EX bar, EY bar directions in terms of EX and EY. And this is the information that is needed to perform the transformation. And to do the transformation, let's say that we want to find UI bar in terms of UI and VI. So what we can do is we can take, let me go back here. So we can take this vector DI and actually take the projection of this vector in the EX bar direction. That is what, that's how we can get UI bar. And to take the projection, we are just doing the dot product. So what we are going to do is we are going to do the dot to get the UI. We are going to take DI and dot with EX bar. Okay. So this is what is done here. So UI bar is just DI dot EX bar. And this is just the algebra. I just put the expression for EX bar that we have here. So EX bar, I put this expression and dotted with DI. And if we do the algebra, this is the expression we will get. Similarly, we can find what is VI bar. So VI bar is DI dot EY bar. So we take this displacement. We take this displacement DI, and in this case, to get VI bar, we dot it with EY bar. Okay, so this is, you can think that this is a projection. VI bar is a projection of DI in the EY bar direction. So to get the projection, we did the dot product again, and this is the expression we will get. And theta I bar is equal to theta I. Now we have these three relationships, 1, 2, 3. We just represented in a matrix form. So we represent it like this here in the matrix form. And now this is the exercise we did for the I node displacement. We can exactly do the same exercise for the J node displacement, and we will have exactly the same relationship. So you can see that we will have UI, same relationship as we got for the UI bar, VI bar, theta I bar. We'll get the same thing for UJ bar, VJ bar, theta J bar. And in this case, these J degrees of freedom will be related to the J degrees of freedom at the J node. And but the form of this relationship is not going to change. And finally, what we did is we take these two matrices and express in a big system. So now I'm putting all these degrees of freedom together. UI bar, VI bar, theta I bar, UJ bar, VJ bar, theta J bar. And this block is actually just this block, 3 by 3 block here. And then I just padded with an additional 3 by 3 zeros, because we already know that these I displacement does not depend on the J displacement. So they're all multiplied by zeros. And similarly, UJ bar, VJ bar, theta J bar, this is this block. This is this matrix here is this block here. And this is padded with zeros here. And now what we have done is we have represented the local displacement in terms of the global displacements for that element. So these are the displacements in the global degrees in the global coordinate system. These are the displacements in the local coordinate system. And they're related by this matrix that we are going to call it T, or a transformation matrix. It's very important. What we have done is we have represented the displacement, but actually the same thing can be done for forces, because forces and displacements both are vectors and both follow the same concept of vector algebra. So we could have written exactly the same expression for the forces also, and I'll show you in the next slide how to do that. So let's complete this first, so this is the relationship between the displacements. So you can see that this is the displacement in the local coordinate system, displacement in the global coordinate system for the element, represented by this T matrix. I'm calling it transformation. So this is a 6x6 transformation matrix. And this is how we can represent in the compact form. So we can write D bar is equal to T times D. And we can also do the inverse process. So we can take, if we want to find D in terms of D bar, we can say D is equal to T inverse. So you can put an inverse here and say T inverse D bar. It's a 6x6 matrix, so it's a square matrix. We can take the inverse. But the one important observation here is that this transformation matrix T is an orthogonal matrix. So what does it mean? It means that the inverse of this matrix is equal to the transpose. So really, we don't have to do the inverse. We can just take the transpose, and that is equal to inverse. So we can write D is equal to T transpose D bar. Okay. And another important observation is these lambda x and lambda y are nothing but, if you remember to calculate how to calculate those orientation angles. So lambda x is nothing but C, and lambda y is nothing but S, where C is cos theta and S is sine theta, where theta is the orientation angle. And we have talked about how to calculate the orientation angle for truss members, exactly the same way you calculate the orientation angle for frame members. And using the same algebra, we end up with exactly the similar relationship for forces in the local and global coordinate system. So you can see that this is the force vector in the local coordinate system. This is the force vector in the global coordinate system. They're represented by the same transformation matrix because they follow the same vector algebra. And finally, we can see that we can write P bar is equal to T times P, or P is equal to T transpose P bar. So this is the same similar algebra as for the displacement. So there is not a difference between the transformation rules for displacements or forces, because they follow the same idea. Again, important to remember that this transformation matrix is an orthogonal matrix. And finally, this information will help us to actually relate these two quantities. Now we can go and relate these equilibrium equations written in this local coordinate system and the global coordinate system. Okay, so we can start from here and go here. And this is something we have already done for 3D trusses. So we follow exactly the same idea here. So in local coordinate system, we can write P bar is equal to K bar times D bar plus PO. So we know what is K bar, we know what is PO. So in the local coordinate system, this is just a beam element, equilibrium for the beam element. Okay. Now we want to convert this to a frame element. So first what we do is we pre-multiply both sides by T transpose. So I put T transpose on both sides. So we get this expression here. And then finally, we are going to use D bar because we want to get rid of D bar here. So I'm going to use D bar is equal to T times D. And we can see that T transpose P bar is nothing but P. So we are going to use this expression here. So I'm going to replace this by P and D bar by T times D. So I will end up with a final expression like this. And if we relate this final expression to P is equal to KD plus P0, you can see that our K is nothing but T transpose K bar T, and P0 is T transpose P0 bar. So now you can see that this is the K is the stiffness matrix in the global coordinate system, and P0 is the fixed end forces in the global coordinate system, and they're related to actually the quantities in the local coordinate system like K bar and PO bar. So now we have these two things that we need. So you can see that this is the final things that we actually try to assemble when we are trying to assemble the global system. And this is the key calculation that has to be done. One important observation is this is exactly the similar kind of calculation that you have done for 3D trusses and actually even 2D trusses. So you can see that the overall format of the equations doesn't change. Of course, the value of T and K bar will change, but equations, like the form of the equations, remain the same. And this is a very important concept. It turns out that even we have like a 3D frames, we will end up with the similar equations. What will change is only k bar and t, but the equations, like how they're related in the global and local coordinate system, they're still going to remain the same. Okay, that's the reason it's important to follow this idea of transformation, because once you know how to transform, like from local to global or global to local, then the same idea can be used for different cases. So now one important thing is, now you have to realize that if you are trying to write a program for frame elements that can work with 2D frames, you have to have a function that can actually calculate the element stiffness matrices like K and P0 for all the elements in that frame. Okay, so it means that you need to write a function that can give you K and P0, and that is something you have to do as a part of your project. So you have to create that function, and after you solve the problem, you also want to calculate the forces. But what will happen? So what we want to do is, in our case, we want the forces to be in the local system. So if we want to calculate the forces for the frame elements, what we want to calculate is P bar. Okay, so this is what we will try to output in our calculations. The reason is, these P bar forces make more physical sense, because you can make sense of these numbers. If you express the forces in the global coordinate system like P, they will not much. We will see that they will not make much physical sense. Okay, so P bar makes more physical sense when we try to express forces, but K and P0 is needed to solve the problem. So we have to write two functions. One is to calculate the stiffness matrix and PO, and the other function is after we solve the system to calculate this P bar. So these are the two functions you have to write as a part of your project. So let me give you an overview of these functions. So one of these functions will be frame element stiffness 2D. And so this is, you can think as a counterpart to the truss element stiffness function that you have written. So in this case, the inputs will be coordinate I, coordinate J, E, A, I is the moment of inertia, and Q and P. So I'm assuming that Q is the distributed load and P is the point load that is acting at the center. So we can include many other loading conditions. So these are the only two loading conditions that I'm considering for now. So Q is the uniformly distributed load and P is the point load at center. So given all this information, you want to first calculate L, lambda x, lambda y. After you calculate these three things, you can calculate the transformation matrix because you already have the equation. And then finally, you can calculate the K bar. So this is the beam element stiffness matrix in the local. So this is the local coordinate system. You're working in the local coordinate system. So just calculate K bar. And finally, do this transformation to calculate the frame element stiffness matrix. T bar is K bar. So K is T transpose K bar T. Okay, so this is the global to local transformation, and this output should be a 6x6 matrix output. So this is a 6x6 matrix here, and then next you will calculate PO bar. So PO bar will include the contribution of two forces, Q and P, and these are in the local coordinate system. So you can use your fixed forces, that chart, to figure out what this PO bar is. And then you will transform it to the global coordinate system by just multiplying by T transpose times PO bar. And this is a local to global transformation, and the output should be a 6x1 vector. So these two things are your output, K and P0. And this is something then the program will use. So these are the quantities that will be assembled in the global system. So you have to create this function as a part of your project. And the second function that you have to create is actually force element force 2D. So in this case, actually, you're trying to find the member force after the calculations for the displacements are done. So after solving the problem, you want to find the member forces. And as I said, we want to calculate the member forces in the local coordinate system. So we want to do this calculation. P bar is equal to K bar D bar plus PO bar. So this function is straightforward. First, again, you will calculate length lambda x lambda y, find the transformation matrix. In this case, there is an additional input to this a function, that is d bar. So actually it's not, there's no bar here, so this is d. So there's a typo here, this should be d. And actually, so the input is actually the displacement in the global coordinate system. So actually we take this d and convert to the displacement in the local coordinate system. So we can convert, we can find d bar by doing this transformation, t times d, and this is nothing but this relationship. So we already seen that. So d is given, we want to find d bar, so we can use this relationship to find d bar. And after we have the d bar, we can use this to find our forces p bar. So p bar is k bar d bar plus po bar, and po bar is the fixed end forces in the local system. So you have to again recalculate them. And this will be the output p bar, and this should be a 6x1 vector. Okay, so 6x1 vector means this is actually you're outputting these 6 numbers: pxi, pyi, mi, pxj, pyj, mj. So you have all these numbers here. So these two functions, after if you create these two functions, then you will be able to use the Matlab code for 2D frames. And to give you an idea how all these things is going to work, let me show you some examples, and I'll show you my code, and let me tell you how to put together all these things. So first example is actually a 2-bay frame in which I put like a lot of different kind of loading. So you can see that there is some kind of a distributed load on member EF, and there is some member AD, and BE has some loads acting at the center, and there is also some nodal loads. I've also written down the units here. So in this problem, I'm going to use the units of kips and fit. Okay, so you have to be careful with the unit system whenever you're using the code. So make sure that you use a consistent unit system. So for this problem, I'm using kips and fit. And the first step is actually I have to discretize the system and decide on the what are the nodes and what are the elements. So this is how my discretization looks like. So I put like 6 nodes, 1, 2, 3, 4, 5, 6, and then I have 3 columns. So this is the first column, or second column, third column, and 2 beam members, 4 and 5. So these are the members I have in this case. So you can see that the first member is between 1 and 4, the second member is between 2 and 5, third member is the connectivity is 3 and 6, fourth member the connectivity is 4 and 5, and fifth member the connectivity is 5 and 6. So these are the members, 5 members that I'm using in this problem. And finally, the degrees of freedom are automatically defined by the program, and so these are the degrees of freedom. So what the program does, it goes to each node in an incremental fashion and assign the 3 numbers. So in this case, the U degree of freedom is assigned first, then the V degree of freedom is assigned, and then the third degree of freedom, that is the rotational degree of freedom, is assigned. So you can see that this is the ordering of the degrees of freedom. And now we want to actually apply the loads here. And for the loading, you have to be a little bit careful when you are applying the member loads. And the reason is as follows. So if you recall, the fixed end forces, for example, this is the fixed end forces for a concentrated load at the center of the beam. So you can see that in this case, the way we have defined P, so P is positive if it's acting in the negative y direction. Okay, so negative y bar direction. So if you think that if you know the local axis, for example, local y direction, so if the P is acting in the negative y direction, then it's positive. Okay, so because this is the way we define these fixed end forces. Similarly, Q is positive if it's act in the negative y bar direction. Okay, so you have to be careful when you're putting the input data. So input data will depends on what is your y bar direction for a given member, and the important thing is y-bar direction can be, it depends on how you define your connectivity. So let me give you one idea here. So let's assume, like, let's say that we want to figure out, let's say we are looking at this AD element, okay? So there are two ways. I could have chosen two different ways of I and J node, and let me show you the idea here. So let's say that in the first case, we are calling A node as the I node and D node as the J node. So this is the orientation of X bar and this is the Y bar. So you can see that in this case, the way the load is applied, the loading is actually in the negative Y bar direction. So in this case, P is actually 10 because the loading is acting in a positive sense, because we said that P is positive when it acts in the negative Y bar direction. So we are good here. But if I have defined D node as the I node and the A node as the J node, my Y bar will actually then will be in the opposite sense as in this case. So Y bar is in this direction. So you can see that now my load at the center is actually acting in the positive Y bar direction. And so if the orientation of the member is like this, then I have to input the data of P is equal to -10 in the program, okay? So I have to be careful when I'm putting these values. First, I should know what's the orientation of the members. So it means that for the beam member, there's an additional thing you have to worry about. What is the orientation of these local axes? And to help you with this process, what I have done, I have included one more option in the when you plot these frames. So there's an option to actually plot the orientation, and that orientation will depend on the way you are defining the connectivity. Okay, so that's how I'll show in a moment. So let's say that if I'm working with this problem, this is the orientation. When I'll show you this how this Matlab code is working, but I can actually plot the orientation. Okay, so if the way I have defined my connectivity, the orientation is in this direction for these members. So, and the orientation for these beam members are like this. So actually you can think that for this column, this is the I node, this is the J node, this is the I node, this is the J node. For this column, this is the I node, this is the J node. And for this beam, this is the I node, this is the J node. So X is this way. And for this beam, this is the I node, this is the J node. So, and I have defined a function to plot this orientation for you. Let me show you how this works, and then we'll move forward from here. So this is my Matlab code for problem number 1. And again, I have 5 elements, so I put NELE is 5, number of nodes are 6. Node degrees of freedom are 3 because there are 3 degrees of freedom at every node. I define my 6 coordinates and the connectivity for every member. And if I go down, you can see that there is a function. I will provide you this function. The name of the function is plot 2D frame, and this function actually plots the frame for you. But there is an interesting variable in this function. I'm calling it a local axis flag. When this flag is 1, it plots the local axis for every member. Okay. So let me show you how this works. Like I'm creating the breakpoint here to show you the result for this, and I'm running this code. So you can see that this is the local axis for these members, and these are the same things that I've just shown you on the slide. And the reason was because the way I have defined the connectivity, because this was the first node, second node, third node, 4, 5, 6. So you can see that the first member is between. I've defined the connectivity as 1 and 4. Okay, so. But if I flip the connectivity, I could have defined 4 and 1 also. So I could have defined this as 4 and 1 for the first member, let's say. And if I plot it again, then you will see that the local y-axis has now changed, because this is the I node at the top and the J node at the bottom. So you can see that the axis has flipped now. When we are defining that load acting at the center for this member, we have to be careful. Okay, so we have to be careful because we have to first know what is the orientation of the member. So once you decide on the orientation of the member, you can define the other data accordingly. So the best way to think is first define whichever way you want to define the connectivity, And based on your connectivity, you have some orientation. And for that given orientation, you can define your loads. Okay, this is the way to think. So let me go back and let me put the original 1, 1, and 4. So I have the correct orientation, the one I have defined. So in this orientation, if I use this orientation, you can see that for this column, the load should be, the P should be, so if I go back here, P should be 10. Okay. But for column BE, now you can see that the load is acting in the positive y direction, because positive y direction is in this direction. So I should be using the P value of -20, okay? Because now the load is actually in the negative sense. The Q value for this beam member should still remain 2, because the load is acting in the negative y bar direction. So we are good. We can still use Q is equal to 2 for this case. So we have to be careful when you're defining these member forces. And they are defined with respect to the local axis of the beam members, or these frame members. Okay. And this is the idea here. And once we get the so we can go ahead and solve the problem. So after I solve the problem, these are the displacements of the nodes, and these are the member forces. So I can you can see that I'm reporting the member forces in the local coordinate system. So these are in local coordinate system for a given member, because we already know what is the local axis. And these numbers, whatever these numbers are, they are with respect to the local coordinate system. And I can also plot the deformed shape. So this is the way the system is deforming, and you can see that there's a lot of lateral motion in this frame, and because of the way frame is supported. So you can see that here there was a roller. So you can see that this node is moving to the right, just because of there's a roller here. And this is plotted with the magnification factor of 10. So let me show you my code here. So if I go back to my code, so you can see that I'm using this frame element stiffness 2D. This is the function that I was talking to you that you have to create as a part of the project, and it has some variables. So I will provide you this this code. So you can actually test it out yourself after creating this function. And after you solve this problem, the solution remains the same. The solution strategy remains the same as for like the 2D trusses or 3D trusses. And then we calculate the member forces. And this is the second function that you have to write. So you have to write frame element stiffness 2D function and the frame element force 2D function. Okay. So this function actually calculates the member forces in the local coordinate system. I will not show you my code, but you have to write this code yourself. And I have already given you an idea how to write this code and what should be in this code. And finally, after solving this problem, I actually try to plot the deformed geometry. So you can see that when I'm plotting my deformed geometry, the local axis flag, I have turned it off because I don't want to plot the local axis anymore. And this function can plot the geometry of the deformed geometry. So this is the deformed geometry. And another important thing I want to tell you is, if you look at my plot function, it's not a straightforward function anymore. I have used some tricks to get this deformation right, but don't worry about them right now. You can just use my function and don't worry about what's the idea behind it. Okay. Maybe if I get a time, I'll go into the detail of how to plot these kind of frames. But for now, you can just use it directly. And if you provide the input data correctly, you should be able to use it in the careful way. And let me close this plot here. Another thing I want to point out is that there is another variable that I'm inputting, and that is the IV. So you can see that now the member properties are area, modulus of elasticity, E. IV is the moment of cross section, moment of inertia of the cross section. QV is the uniformly distributed load vector. PV is the point load, okay, acting at the center. So point load at midspan. So these are the things that you need. But for plotting the frame, I'm also using this IV. The reason I'm using it, I'll show you in the next example when I'm using this. This actually tells me whether the member is a beam or is a truss member, because if some members are like truss member or braces, I just plot them in a different color. So this is just used to indicate different colors in the plot. Okay. So let me move forward. So this is how we can solve this problem, and we can get our answers. And actually what we can do is there's another way to solve this problem. So in the second case, what I'm doing, I'm adding more elements or more nodes. So what I'm doing is I'm subdividing every element into two elements. So instead of considering one column from this node to this node, now I'm considering there are two columns. So I'm actually adding one more node at the center, and I've added one more node at the center of the beam also. It's perfectly fine. So what I have done is I have introduced more nodes. It means that I have introduced more degrees of freedom. Okay, so now my degrees of freedom, the total degrees of freedom in the system are 33 degrees of freedom, because there are 11 nodes. So 11 times 3 is 33. And so this problem, I'm getting more information because I'm also calculating displacements at these center nodes also now. These displacements I was not calculating in the earlier case. One important observation is that now if you look at the member loads here, so if you look at these member loads that were acting on AD and BE, so they are now going to be nodal loads. So you can think now that 10 and 20 are directly going to apply the nodes. Okay, so they're not going to apply at the members now. So you can see that 10 goes in the direction of 10, and that 20 goes, or you should put P13 is equal to minus 20. Okay, because that goes in because the 20 is acting in the negative 13 direction. Okay, so in this case there will be no load that is acting at the midspan of the member. Still, these 9 and 10 elements will have Q, and that is acting vertically downwards. So there is a distributed loads on member 9 and 10, but there is no concentrated forces that are acting at the midspan of members for any of the members. So this is an important difference, and you have to be careful when you are inputting the data. But if we input the data correctly, it turns out that we should be still able to solve it. I'm still again showing you what are the local X and local Y axis. So because the member loads are now acting on these two beam members, and you can see that the Q was acting in the negative Y direction. So Q is fine. So we can just use the Q value of 2. We don't have to flip the sign of Q. And because that's a positive direction. And we can solve the system. And if we solve the system and we get the displacement at the same positions, it turns out we exactly get the same displacement if we look at the same positions. Okay, so I'm still looking at the displacement at these A, B, C, D, E, F, and we end up with exactly the same result. Of course, we have more displacement at these middle nodes also, but I'm not showing you those displacements. And it turns out we exactly get the same solution. So there is no difference. The deformed shape looks similar. Okay, so there is no difference in the solution, but we have more information in this case. And I'm also going to provide you this file here. So I have added more, like for example, this is the second case where I have added more elements. So you can see that I have added more coordinates and more elements, and I solved the problem. You can see that in this case, point load at midspan, there is actually they're all 0. Okay, so there is no point load at midspan in this case. None of the members have point load at midspan. And I can again go ahead and plot this and show you the answers. So you can see that this is how this system deforms, and this is how it looks like. So these are the local X and Y axis, and this is the way the system is deforming. So I hope this helps you to understand that, okay, we can add more like nodes to every element, and we can do like a better analysis, or if you want more information for an element, we can keep adding nodes. One important comment I want to make is that if you look at the commercial programs like SAP or any other commercial structural analysis program, actually they try to subdivide a beam or column into, let's say, 10 to 12 elements. Sometimes you don't have a control on how many elements they're dividing, and they don't even show you. But internally, they actually try to divide these beam and column elements into like 10 to 12 elements, and then they do the analysis. Okay, but this is the way is done technically. But all this process is automated, so they had to, there's a logic to create these nodes, divide them, and so on and so forth. And so if you build a logic, you don't have to do it by hand. But for our homeworks and our projects, we are putting all this data by hand, so it becomes a little cumbersome. But if you can program it, you can keep adding more nodes and more elements. There is no restriction on the number of nodes or number of elements that we can add. And the more information we want, we can add more number of nodes and elements, and we can get more information. The next example is actually the same frame, but what I have done is I have added bracings here. So let me tell you what's the meaning of bracing. So when I'm adding two members, one from A to E, the other is from C to E. And you can see that the way I have put it here is like I'm denoting this red dots. These are hinges, okay? Hinges means there is no movement transfer between this member and this connection here. Similarly, the movement cannot transfer between this member and this connection. So actually, this member is like a brace member. Brace member means it can only carry axial forces. So it's like a truss member. So a bracing is nothing but a truss member. And the reason it cannot carry any moments because of this pin connections, okay? So, and we want to actually now include the bracing in our analysis, these bracings. The easiest way to do is actually, so if I go back and look at the stiffness matrix of a beam element, let me go back to the very first slide. So if I look at this stiffness matrix of this beam element, if we want to construct like a brace element, all we have to do is we have to put the I value to be 0. If I is 0, all these beam coefficients will disappear, and we will only end up with EA by L entries. And this is like a brace member, okay? Or this is just like a bar member or a truss member. And truss member is a bracing member. So when we say a bracing, it's a truss member that can only carry axial forces. And so you can see that we just have to put the I value to be 0, and A value has to be there, okay? We cannot have a 0 A value for a bracing member. So this is an assumption. So when we say bracing member, we are assuming that the member can only carry axial forces. It cannot carry shear or moment. And the way to do is just put the I value for that member to be 0. And this is the way I have done in my code. So when I run this problem, the connectivity and nothing is changing. So I'm still using the same connectivity, but I have added 2 more members. And the 2 members are added between A and E and C and E. And I have provided the area of braces. So you can see that I don't need any other information for the braces. I just need area. I don't need the moment of inertia. Okay, and all the other properties are here. And I use this properties and solve the problem. These are the degrees of freedom. You can see that even the degrees of freedom are not changing, and the node numbering are not changing. So nothing changed. But what has happened? There are 2 more members. So the total number of members are 1, 2, 3, 4, 5, 6, 7. 6, 7 are the braces. Okay. And I can solve the problem. So these are the orientation of these members. Again, orientations are necessary to define the member loads correctly, because the member loads are actually in the local axis. They are defined with respect to the local axis. So this is the local axis. So this is not changing. So my definition remains the same. And there is no member loads on the bracings, okay? Because bracings only carry axial forces. So we should not apply like a uniformly distributed load and things like that on the braces. So that's not the usual practice. And finally, these are the solutions. Uh, Again, because you can see that the bracings, in my case, actually what's happening here. So for bracing, this bracing number 6, this was the I node, and the 5 was the J node. So you can see that this is I, this is J. And for bracing number 7, the I node was 3, J node was 5. So you can see that so x-axis was like this. In this case, the x-axis was like this. And if these are the forces in the, so the last two forces columns are the forces in the brace members. So if you think carefully, pxj is 35, so this member is under tension. So member A is under tension, and member C is also under tension. Okay, so these two braces are under tension for this system. And if we draw the displaced shape, this is how it looks like. So now you can see that the lateral deformation in the frame has reduced, and this is what the bracings are used for. So bracings actually help to reduce the lateral displacement of a structure. And finally, you can compare this deformation with the deformation with the unbraced frame. So you can see that there's a lot of reduction in the deformation. I'm again using a magnification factor of 10. And you can see that the bracings I'm plotting by pink color. This is just to remind that these members are actually bracing members. And that's the reason there was another input variable to the code. So let me show you the problem, the example problem 2 here. So there's another input variable to my plot 2D frame that was IV. So this variables actually I'm using in this function to determine whether a member is a bracing, or like as a truss member, or a bracing member versus is a beam column member. Okay, and that's the reason there is another input to this function. So if you use this function consistently and carefully, you should be able to run it without any trouble, and you should be able to plot the results with this function. So let me show you this result finally with this. So you can see that these were my local coordinate systems for these members, and this is the displaced configuration for the system. And again, the pink color members are the bracings. So what I'm going to do is I'm going to give you these example problem files. So you will have something to start with. So at least you know what are the results for these cases, because the results for these cases will be presented on these slides. Okay, so what you can do is you can create these two functions, frame element stiffness and the frame element force 2D functions, and try to reproduce these results. So try to reproduce the results for example number 1 and example number 2. And if you are able to reproduce the same results that I have shown here in these tables, this means that you have done the analysis correctly. And after you have done the analysis correctly, you can go ahead and use the results to solve the problems for your final project. And for the final project, you have to solve 2 frames. So the first problem is actually solving a movement frame. I'll provide you the details of the problem later on, but you have to solve like a 3-story by 3-bay movement frame in which there is some lateral loads are acting, and there is some uniformly distributed loads are acting at every floor. And for the column members, the sections are W14 by 120, area and I is given to you, and the units are inches. So make sure that you use the consistent unit system. I think in this case, try to use kips and inches. And for the beam members, all the beam members have section W24 by 76. Area and I is given to you. And E is 29,000 KSI for all members. So again, because some of these dimensions are in fit, so make sure to convert this fit into inches. Okay. Similarly, this loading is given in fit, so make sure that you put the loading in inches to get the correct results. And I'll ask you to output some of the results, and I'll provide that detail in later on. And the second problem you have to solve is like a base frame. So it's exactly the same frame configuration, but I have added 6 bracings. Okay, so this is the way. Sometimes they are known as K bracings. So I have added these brace members in this frame, and you will have to analyze this frame using your code. Again, to model a brace member, you have to just put the I value for that member to be 0, but you have to still provide the area to that member. Okay, this is the trick. So you can use the same code to model both frame members and the brace members or the truss members. And truss and brace members are the same things. And the properties here for the columns and beams are same, but I also provide you the brace members. So brace members are W10 by 30 section. Here we are thinking like these are like steel beams. Okay, so area is 8.84 inch square in this case. And the units we are using, again, be consistent, try to use kips and inches, and E is 29,000 KSI for all members. So this is what you have to do for your project. Create those two functions and try to solve these two problems. And I hope that everyone should be able to do these problems carefully, and make sure to first try to reproduce the results for some of the examples that I've shown you earlier. And that is just to make sure that your code is working correctly. And then you can go ahead and solve these two problems. And these are the things you have to do for your project. And with this, I would like to end this lecture today. And as always, if you have any